conjugate to a finite subgroup gamma inside of OM, which is the subgroup G0 fixing 0. So if you look for finite subgroups of this motion group, they're actually all determined by the finite subgroups of this subgroup fixing the origin. So the point fixed is this barycenter or center of mass, exactly as it was in the two-dimensional case. The same argument works in the n-dimensional case. So when the classification of finite groups of this reduces to the classification of finite groups here, which is an interesting problem, and has only been solved in very few small n cases, n equal 2, 3, and 4. So we did last time the finite subgroups in your orthogonal group of dimension 2, and we found out that they were of two types. The first type, 1, was we let gamma plus be equal to the gamma in gamma whose determinant is 1. So the rotations in gamma. So the first type was when gamma was equal to gamma plus, and that was, then gamma was cyclic of order n. Generated by the rotation of the smallest angle. And the second case was when gamma was contained gamma plus with index 2, so there were elements in gamma of determinant -1, and those groups were dihedral of order 2n, so that this was cyclic of order n, and everything in the non-trivial coset had order 2 and was a reflection, and the reflections conjugated elements in the cyclic subgroup to their inverses. So I could write if cyclic of order n, and that r rotation by theta, r inverse is equal to rotation by theta inverse for all r in gamma minus gamma plus. R squared is equal to 1. Now you get a nice picture of these groups if you consider regular n-gons, because they're preserved by these groups.